Hi, welcome back. In this video, we are going to talk about inference of the mean. We're actually going to do an example using this situation. Researchers tested 150 farm-raised salmon from 51 farms in 8 regions of 6 countries for organic contaminants. They found the mean concentration of carcinogenic insecticide Mirex to be 0.0913 parts per million, with a standard deviation of 0.495 parts per million. As a safety recommendation, the EPA recommended screening value for Mirex is 0.08 parts per million. Are farmed salmon contaminated beyond the level permitted by the EPA? So to start this question, or to start this problem, we need to start with the question posed here: are they contaminated beyond the permitted level set by the EPA? And this is going to be a hypothesis test. So to do this hypothesis test, the first thing we want to do is identify the parameter of interest. So here we are looking at the variable x, where x is the Mirex level in an individual salmon. And the units are parts per million. When I identify that parameter, I want to make sure that I also identify the units along with it. I want to start by thinking about what the null and alternative hypotheses are. So I'm really interested in knowing whether or not farmed salmon exceed this level. So that is going to be that I am looking to see if the mean level in salmon is greater than the EPA 0.08 parts per million level. So I need to start by assuming that it is equal to 0.08 parts per million. This gives me a null hypothesis mean of 0.08. And if we are remembering back to what we did with proportions, I would then need to come up with what my standard deviation to go along with that is. But we don't actually know the standard deviation of this level. They just gave us a level. So I don't know the true standard deviation. I only know the true or assumed mean. But I do have some information from my sample. So we tested 150 salmon. So N is 150. And of those 150 salmon, I found that the mean level of insecticide was 0.0913 parts per million. And this sample had a standard deviation of 0.0495. Now, this is my sample standard deviation. Because I don't know this, I'm not going to be able to use a T or a Z distribution. I'm going to end up needing to use a T distribution. So because I'm going to end up needing a T distribution, I am also going to need to find my degrees of freedom, which are N-1, so 149 in this case. And because I don't know the standard deviation of the population, I'm going to need to estimate that. So the standard or the mean of my sampling distribution based on the central limit is the mean of the population, or 0.08. The standard deviation I won't be able to find, so I'm going to, for the sampling distribution, I'm going to use the standard error, which will be estimated with S sub x divided by the square root of n. If you plug S sub x and n into your calculator, you will get that this is approximately equal to 0.004. So the next thing I need to do before I can really proceed with the test is I need to check my assumptions. So the first main assumption I need to check is independence. So the first piece of this is that I want to know if my sample is a random sample. And it's not exactly a random sample. But they didn't tell me that it was a random sample from the population. But they did tell me that they're from 51 farms in 8 regions of 6 countries for organic, or that they tested. So it seems to be representative. So we are going to say that while it's not random, it is likely representative, which is okay. My sample size is 150, which is less than 10% of all farm-raised salmon. So we meet the independence criteria. When I'm looking at the sample size for condition for the central limit theorem is really where this comes in here. My population here, I don't know whether the population is normal. So the population is not normal, but N is 150, which is greater than 30. So the central limit theorem is okay. Because I don't know this, I'm not going to be able to use the Z distribution, but conditions have been met. To perform a 1 sample t-test of the mean. Okay. So now that I've checked my assumptions and I've stated that I'm going to perform a 1 sample t-test of the mean, I can move on to finding my test statistic. Now, we already talked about the fact that because I do not know a population standard deviation, I can't find the true standard deviation of my sampling distribution. So this is an estimate of my standard deviation of the sampling distribution. So I'm going to use the standard error. And to account for that additional uncertainty, because this is much more uncertain, my test statistic is going to be a t-value instead of a z. So I'm using the t distribution. The formula is very similar. In this case, it is x bar, so my observed minus the mean divided by the standard deviation or the standard error. In this case, it's standard error because I don't know the truth. And when you plug this into your calculator, you get 2.80, about 2.80. If you were to use your calculator, you end up getting 2.79588 is what you actually get exactly on your calculator. But this rounds pretty nicely to 2.80. Okay, so now I need to find my p-value. So instead of drawing the normal distribution, I'm going to draw a t-distribution, which looks just like the normal distribution, but I'm going to label it with t and the degrees of freedom. So this is 0. Based on my alternative hypothesis here, this is a right tail test. So I am going to graph my test statistic here, 2.80, and this area here is my p-value. So 2 ways to find this p-value. I am going to do both on my calculator. So the first is that I can use TCDF here, which is option 6. My lower limit is 2.80. My upper limit is 1E99. And I have 149 degrees of freedom. And that gives me 0.0029. The other way that I can actually get my test statistic and my p-value is that I can go to stat, test, t-test. It's the second option. And what I need to input is my assumed true mean, which is 0.08. My sample mean, 0.0913. My sample standard deviation, 0.0495. My sample size, 150. And then the fact that my alternative hypothesis is that the mean is actually greater than that assumed mean. If you have data, you can input your data into a list and it will actually get the mean, standard deviation, and sample size from that. So I hit calculate, and I get the test statistic is 2.79588, which is right there. You do need to always make sure you include this formula. And the p-value is 0.0029, which I also got using my calculator. You do also need to make sure you include this drawing here. All right, so this is my p-value. So I got my test statistic, my p-value. I'm ready to start writing my conclusion. So before I jump into the conclusion, I want to think about this. This is about 3 out of 1,000. All right, so let's write my conclusion. So we want to start out by interpreting the p-value. So our p-value is 0.0029. So if the true mean level of Murex in farm-raised salmon is 0.08 parts per million, I would expect a sample of 150 salmon to have an average Murex level of at least 0.0913 about 3 times in 1,000. So what this is really saying is it is saying that what the p-value is a conditional probability. This is a conditional probability. This is the probability that we would get a sample mean that is greater than or equal to 0.0913, given that the true mean is 0.08. If this is true, this is what that probability is. 3 times in 1,000 is very small. So because the p-value is so small, I reject the null hypothesis. So now that I have rejected the null hypothesis, I'm going to say what my conclusion is, what I'm actually saying, which is that I am supporting, there's strong evidence to support the alternative hypothesis, and meaning my answer to the question is that they seem to be above the level permitted. So there is strong evidence that the true mean level of Murex in farm-raised salmon is above the level permitted by the EPA. So this is now my conclusion to the hypothesis test. In the next video, we're going to take this one step further and make an estimate of, now that I believe it's bigger than 0.08, I'm going to now look at how much bigger than 0.08.